Okay, so now let's do something related. Okay, so we do not want to compute the expected value of a function, but let's say, okay, suppose we want to compute the following integral from a to b. Okay, this is the integral fx dx. Okay, so we are going to be computing the value of the integral this time. Okay, so we are not computing the expected value. We just want to compute the basically the integral of this function fx from a to b. Now, okay, so this is where the Monte Carlo will come into this picture. So we will be using Monte Carlo to evaluate this integral. Now, it can be shown that, okay, it can be shown that, and which we will show, the expected value of the estimator, okay, estimator, we call it the estimator because it estimates the value of this integral of the estimator 1 over n from sigma I 1 to n. Okay, so we will be drawing basically n samples. fxi probability and divide by the probability of xi is equal to that integral. Okay, so I would like to draw your attention to a couple of things here. Seems like a simple definition, but we need to be careful. So it can be shown that the expected value, okay, the expected value of this, so not this directly, the expected value of this estimator is equal to this integral. Okay, so in other words, we need to write the expected value of 1 over n I from 1 to n fxi divided by the probability of xi is equal to this integral from a to b fx dx. Okay, now before we prove this, let's understand the implication of this. So here you have an integral that you want to evaluate, but you cannot evaluate it using analytical methods for whatever reason. Okay, maybe you don't want to, or maybe you cannot do it. You cannot analytically compute the integral. Okay, but you need the integral, kind of like our rendering equation, the integral in our rendering equation. On here, what we say is that if you actually compute a discrete summation of samples, basically, so these are xi's are your sample points. Okay, so if you compute the sum of these, but important thing is you divide the value of the function at xi by the probability of that. Okay, so if, for example, if the probability of getting a certain xi is large, you penalize it by dividing it by a larger denominator. If the probability of a certain xi is small, you then kind of reward it by dividing by a smaller denominator. Okay, so this division by the probability is important here. Okay, so you have n samples, you add up their contribution using this form, and then you divide the result by n. This will actually give you not exactly the value of the integral, but the expected value of this is going to be your integral. Okay, obviously with more samples that you have, you are going to reach a better convergence to the true value of the integral.